Welcome back to ECE 501B. Homework number 4 is due a week from Friday, and next week at this time you won't see me, or you shouldn't be seeing me. If you do see me, that will be interesting. But next Wednesday we will not meet in class, and I won't be in office hours, and maybe by next time we meet, maybe I'll have some alternative suggestions as to what might happen with office hours or with material. Today what I want to do is, I'm excited, now we get to go into another chapter, chapter 6, and this is dealing with inner product spaces. And so we'll talk about an inner product, and it's a generalization of the dot product. It's not just the dot product, and that's what makes it sort of interesting, is now we're generalizing that dot product idea or concept, and it is nice because we can look at this inner product in a more general or a more abstract way, and that's what we'll try to convey. But first is, what are we doing with an inner product? Now this actually, we haven't really talked about length or closeness or angle with respect to vectors, and that's what this inner product allows us to do. We'll state the properties that we want this inner product to possess. Then if we combine a vector space and add to it an inner product, then we create an inner product space. And a lot of times we'll just say V, and it'll be implied that that's now an inner product space, that we've defined an inner product and attached that to our vector space. We'll give some example inner products that hopefully will get us thinking beyond just the dot product. We'll look at orthogonality. Now you're really questioning why you're sitting in this class. We're going to discuss Pythagorean Theorem. But now it is motivated by the fact that we are breaking up something into orthogonal components, or we have two vectors that are orthogonal. That allows us to then have the Pythagorean theorem. And then we'll look at orthogonal decomposition and a couple of inequalities, the Cauchy-Schwarz inequality and the triangle inequality. I'm not sure we'll get all that way today, but that's where we're headed, and that's what chapter 6 deals with, is inner product spaces. And in particular, like I said, they tell us a distance and a closeness. If you give me two vectors, and now you could think of these in R2 or R3 simply to give something that you can, or to think about it, to give you some intuition. Now, what's the length of that vector, or what's the distance between the tail of that, or the origin, and the head of that vector? What's that distance? And then if I have two angles, are they close? Are they separated? Are they actually orthogonal to one another? And you might just look and see this. The book is now talking in this chapter about the Supreme Court. So I'll just give you that under the table clue, and you can now go read about, actually they're or a lawyer comes in front of the Supreme Court and he uses the word orthogonal, and the justices are saying, wait a minute, what word was that was just used? It's kind of cute. Anyway, you might look at that and see if that puts a little different spin on the Supreme Court than what's been in the news lately. So hopefully it's a little bit lighter side to the Supreme Court discussion that you haven't seen until maybe you start reading chapter 6. And it deals with orthogonal. So let's now do or define or create the rule for an inner product. The inner product, obviously I was grading or something when I quit writing on the tablet. The inner product between two vectors we'll call those V and W, and those are in a vector space V. Now we're simply establishing the notation. I'll try to be consistent and use brackets. So this is now open bracket V, W, and that's actually, the order is important, and I'm not going to use parentheses because then you might get confused with it being a list or an ordered pair. So now when I use the bracket, that means that we're talking about the inner product between two vectors. And an inner product is a rule that takes an ordered pair again, it's important how you write that. V first, then W is different from W first, then V in this definition. It takes an ordered pair of vectors, which we might write as VW in parentheses, to a scalar. And the scalar is given to us by bracketing V and W, and that result will belong to whatever scalar field we are dealing with, the reals or complex. So that's the rule. We want to take two vectors and create a number, a scalar, from those. We also want this inner product to possess certain properties. So when it has the following properties. The first property can be described as positivity, meaning if you take the inner product with itself, if you use the inner product or apply the inner product to a vector itself, so now you say V comma V, then that's going to be greater than or equal to 0 for all vectors V. So we need the inner product to satisfy this positivity property. We also want it to have a property of definiteness. By that we mean that if the inner product of a vector with itself is equal to 0, that's going to occur only when the vector itself is the identity vector, or the 0 vector. So if and only if V is equal to 0, we get the inner product is equal to 0. We also want to have additivity in the first slot. So that now, relative to this inner product, there's two slots, the first slot and the second slot. And that allows us to talk about which of the vectors we're referring to. But here, if we want additivity in the first slot, what we're meaning is if we have, let's say, U plus V in the first slot and W in the second, then we want that to be equal to the sum of two inner products, U with W and V with W. And that should be true for all U, V, and W that belong to V. That's what we mean by additivity in the first slot. We also want homogeneity in the first slot. meaning if we have a scalar, A, that's scaling the vector in the first slot, then we actually want to be able to immediately or without change pull that scalar outside the inner product, or have it scale the inner product of V with W. And that should be true for all scalars A and V's and W in the vector space V. Finally, we want this last property, which is conjugate symmetry. So now we want there to be symmetry in the inner product, but because the vectors could be coming or defined over the complex field, we need to worry about the imaginary components of these real quantities. So here we're saying that if we have the inner product of V with W, that's going to be equal to the conjugate, the complex conjugate. There's that star again, but I'm going to use that to be the conjugate. So this is now the complex conjugate operation of the inner product of W and V. And this is true for all V and W in the vector space V. That star, which is ugly, but you'll get used to it, that's different than what the textbook uses. The textbook actually uses the bar, but I might get too sloppy and forget the bar or not include the bar. But just to let you know, this starring to indicate the complex conjugate that I hope I maintain in these notes might be different than what Axler uses. Axler might say, oh, V bar is the complex conjugate of the vector V. Now, it should be clear that some of these properties actually simplify when we're dealing with the real field, or the field of reals. So note that the conjugate symmetry indeed simplifies if our vector space V is a real vector space. And we've already said this in the introductory comments when we were talking about the goals. An inner product space and you can compare that with the vector space. Now the inner product space is a vector space, let's say capital V, plus, or that enjoys or has an inner product rule on that vector space, plus an inner product rule on V. So that's what chapter 6 is dealing with inner product spaces. So we have to be comfortable with this concept of inner product. Let's now look at an important example. Suppose we now have f to the n, where f again could be either real or complex. And let's now put it, or create, or define the following inner product. So now if we have the inner product, and now these v's are components of the vector v. So v1 is the first element, v2 is the second element, up to v sub n. That's in the first slot. So this is now the vector v, and then we have a corresponding w vector with its n elements. Then this is sort of the default inner product. This will be v1 times the conjugate of w1 plus v2 times the conjugate of w2. So here we're matching up component parts of the v and w, except now the components in the second slot we need to conjugate before we multiply those to their corresponding element in the first vector slot component. So this is now up to v sub n w sub n conjugate. And this is actually the Euclidean inner product, so that it looks like what you're used to thinking maybe in the real space with Euclidean distance, or the Euclidean inner product with the above rule. Or the Euclidean inner product is with the above rule we can now say that the inner product of v with itself is now the norm, the 2 norm of v squared. So the inner product of a vector with itself gives you the square of its 2 norm. The squared Euclidean length of the vector v. And that is kind of a warm and fuzzy. So that's the 2 norm. Or we can think about the inner product being consistent with the 2 norm. Also, if our vector space is actually r to the n, so now we're dealing with a real vector space, then if we have the inner product of u with v, that's now just u dotted with v, and I don't have to worry about conjugating elements since I'm dealing with real numbers or real scalars. So this is now the dot product. And that's the standard behavior that we've come to expect from our geometric thinking or geometric vector spaces. So that's sort of the traditional way of thinking about an inner product. Let's look at some others that try to generalize this concept or give us a more broad perspective on this concept. So here, let's look at some other inner products. suppose we're still dealing with f to the n, then you could create somewhat similar to what we've seen before, but now we can actually scale each of those component products with a positive scalar. C1 V1 W1 star plus C sub 2 V2 W2 star on up to C sub n V sub n W sub n star, with all of these C sub i's being real and positive or positive real. That's another inner product that's possible, and it satisfies all of those properties that we've defined. Another one, let's say that we're now on, whoops, I don't need to even specialize it yet to reals. Let's just say that this is now nth order polynomials. Then we can define a couple of different inner products on this set or vector space. One, let's say that we have P and Q as nth order polynomials. We could define an inner product to be the integral from 0 to 1 of P of x, Q of x conjugate dx. Another one might be on, let's just make it P sub 2 with the reals. Could be, if I now have vectors v and w, what if I simply evaluate each vector at -1 and multiply that together, add that to now the two vectors evaluated at 0, and each vector evaluated at 1 and multiplied together. That can also be an inner product.
You don't have to take the conjugate for W.
So now we could, but I've now specialized it to the reals. So now I have P sub 2 in the reals, just because now I'm going to start illustrating what this really looks like. But the critical part of this, so the comment was, don't I have to conjugate the w's? And here I avoided that because I'm dealing with the field of reals. But now the key point is to notice that these were second order polynomials, and how many points did I evaluate the vector at? 3. 1 bigger than 2. So 3 is 1 more than 2. If I had, I know that sounds trivial, it is, but it's important here. If I had P3, I would need to evaluate this at 4 locations, and we'll see what that means or denotes as we work through this. So let's look at some examples of this. Suppose that I take v of t and now let that be t plus 1, and suppose that I look at w of t and let that be t squared minus 1. So these are both in P2. So V and W are in P2 of R. Let's now look at the inner product using inner product number 2. Well, all that said is that I need to evaluate these polynomials at 3 points. One of the points was at -1, and what's v of -1? What does that evaluate to? 0. What about v of 0? That's 1, and v of 1, 2. So that's as easy as it is. And then we can evaluate w at those 3 places, or points. W of -1, W of 0, and W of 1. So now the inner product, using rule 2, with v inner product with w is going to be v of -1, w of -1, or 0 times 0. Then I have v of 0 times w of 0, and I add that to v of 1 times w of 1, and the inner product is -1. And that's a valid inner product. So I compare, or I say, what's the inner product of v with w? Using that inner product, it's -1. What does it mean? So we'll develop that in a minute in terms of what does that mean, but how can we think about that? That's what we will get to after we sort of illustrate this with some examples. Yes? So now the question was, why are we only restricted to these 3 points? We are not. I picked these 3 points. You could pick another 3 points and define your own inner product. But it would have to be 3 points. That's the point. That's what I want to make clear. So I'll say that in just a minute. But you could say, oh, I'm going to evaluate it at 0, 1, and 2. And that would be a valid inner product.
So why does it also have to be just 3?
Why? Well, it could be more than 3 points, but it needs to be at least 3 points. So it can't be less than 3. It can't be less than or equal to 2 points that we're using for P2. Question?
Is that because of definiteness? Is there only 2 zeros?
You're way ahead of me, so I don't even know if you listened to that comment or heard it through the microphone, but yes, that's the point, is it's violating one of these properties of our inner product. And the property that it violates is definiteness. So let me try to make that clear. Obviously, it's already clear, maybe to the whole class, but let me make that note. So the note is, so the comment, or I don't think that was a question, was it? I think that was a statement. So the statement was, is that because it violates definiteness? And the answer is yes. It does violate definiteness. So let me just say, to make sure it's clear, that we need 3 values, or samples. We're sampling these polynomials at 3 points and then forming their product at those 3 points. Samples in P sub 2 of R, and that sub 2 is critical to the 3, to define an inner product. If we were in P sub 4. Now I'm really going to test you. We would need to sample the vector if it was with itself, or vectors if they're 2 different, at how many points? What is it? You said 4, you said 5. I feel like I'm in an auction here. Give me 4, give me 5. 5, 5, 6. I can't auction, so what is it? It needs to be at least 5. So let's say at 5 or more values, and then take the inner product of those 5 values. And here's the reason that you already have suggested or identified. Otherwise, we could actually have an inner product, let's say V with itself, equaling 0 without V being identically equal to 0. So we would violate the definiteness property of an inner product. And if that's still not clear, let me just try to illustrate that a little bit more. So if V now is in P2, and suppose that now somebody says, well, I want to define an inner product that is V of minus 1, W of minus 1, and V of 1, W of 1. And suppose that now I say, well, verify or find a counterexample that this is an inner product. Then somebody says, well, there. Is that identically 0, V of t? No, because it varies as t varies. So this is not the 0 vector in P2. So this is, but yet, if I looked at VV, or V with itself, using my definition, I'm just making sure you guys are awake. What do I get? At minus 1 or 1, it's always 0, isn't it? So now I have 0 times 0 plus 0 times 0, and that's equal to 0. So I really am getting a 0 inner product when my V is not identically the 0 polynomial or the 0 vector in P2. And that's because if you just look at my function, what was it? T squared minus 1. It now, if I could draw, there's t squared minus 1, if this is t. Yeah, it's a terrible picture, but it's about as pretty as my stars. But you get the idea, right? You have this quadratic, and now do you see why we need 3 points? This quadratic is possible that it could cross or equal 0 at 2 points because it's a quadratic. If it was a cubic, it could have 3 zeros, so we need to sample it at 4 locations. If it was a 4th order polynomial, now it could have 4 zeros. We need to sample it at 5 places. That's the idea. because definiteness can be violated if we sample at fewer than n plus 1 locations of those vectors. Let's look now at inner product 1 applied to these vectors. Again, we had v of t equaling t plus 1 and w of t equaling t squared minus 1. And the first inner product that we defined for P2 was now this integral from 0 to 1 of v of t times, and here we're dealing over the real so we don't have to conjugate this, w dt. So thankfully these aren't too complicated of integrals. It's now just powers of t. We now have the integral from 0 to 1, and I now have to integrate t cubed plus t squared minus t minus 1 dt. If I did the multiplication right. Or now I have 1/4 t to the 4th plus 1/3 t cubed minus 1/2 t squared minus t evaluated at 0 and 1. Or the lower limits all vanish because I have a t in every term. I now have 1/4 plus 1/3 minus 1/2 minus 1. Or, for whatever reason, I'd done this differently in my multiplication in my notes, but I now had combined these two to give me a minus 1/4, and I'd combine these two to give me what? A minus 2/3. So now I have something a little bit less than 1, negative 1 in value. Actually, it's bigger than minus 1 relative to minus 1. So this is now, if I get a common denominator, I have minus 3 minus 8. Is that true? 2/3. So that this is now minus 11 over 12. And what was our earlier inner product? Evaluating at 3 points. Minus 1. So we're close. They don't have to be equal, but they're giving us similar information, are they not? This inner product gave us a minus, almost a minus 1, and the other one gave us a minus 1. So those inner products, even though they were different, are giving us similar information. Now, let's look a little bit more, but we will start to get a better feel maybe for what this inner product might represent or provide us with. First, let's look at something else. Let's notice that the first slot exhibits additivity and homogeneity. The combination of those two seems to be familiar, having additivity and homogeneity. Thus, for a fixed vector w, we can actually find a linear map. So now if we, using the inner product, if w is fixed, you give me a vector v in this vector space, that's now using this inner product, because of the homogeneity and additivity of vectors in the first slot, this now becomes a linear map from V to F. So if somebody was asking you to give them a linear map, you could now create an inner product and say, okay, here you go, here's a linear map, if you wanted to. That's assuming now that you fix that W, some vector in your vector space. We can also look at properties dealing with the second slot. So we can also prove certain properties about the second slot. First is we can actually show, using the definitions of the inner product, that we actually have additivity of the second slot. Meaning now if I have the inner product of, let's say, vector u in the first slot with the sum of v and w in the second, now what does that provide me with? Well, we haven't yet justified that we have additivity in the second slot. So all we can do is use additivity of our first slot. And how do we get first and second interchanged? Conjugate them. So now if we take this and say, well, let me switch the vectors in the slots, I can do that by the conjugate. So now u inner product with v plus w should equal, based on our definition of the inner product, v plus w with u's inner product conjugated. Well, let's keep that conjugate by itself for a little bit, so that now we have v plus w u conjugated. And now we can use our property of additivity of the first slot inside the conjugate operation, so that now we have v with w plus w with v with u and w with u conjugated. Or now we can distribute that conjugate, and we now see that we have vu conjugate plus wu conjugate. But if we want to get rid of the conjugate, then we need to flip the location of the vectors in the slots. So this one becomes u comma v plus u comma w. And what does that, if I could get them all on the same screen, what does that now show? Now you can see that we have additivity of the second slot by comparing the leftmost with the rightmost entry. So we don't have to show that anymore. We can just claim that we have additivity of the second slot. What about homogeneity in the second slot? That's not quite, well, it's not the same. Now it's actually conjugate homogeneity of the second slot. So if we have a scaled second slot, if we pull that scalar outside the inner product, we have to conjugate the scalar. That's what that means. So we have conjugate homogeneity in the second slot. And we can show that. Suppose now that we have u AV. Now we're scaling the vector in the second slot. Well, we don't know how to work with a scaled second slot, but we do know how to pull it out of the inner product if we get it in the first slot, and we know how to switch the orders, conjugate. So now we can say, oh, A, V, U, complex conjugate. Or, now that's A, since we know that we have homogeneity in the first slot. I haven't done anything with the conjugate. I've kept that outside. But now what happens when I pull that conjugate inside? The conjugate of a product equals the product of the conjugates, right? So now this is going to be A star V U star, but that's now just A star U comma V. And that now says that, oh, if I scale the second slot vector, I can pull that scalar outside the inner product by conjugating it. So I have conjugate homogeneity in the second slot. What else can we do with these inner products? Well, now we can talk about norms. We've defined norms before, but let's look at them now from the lens of inner products. We've discussed various norms in this course, but not all of these norms play nicely with inner products. So from here on out, let's just agree we're going to define the norms, or the norm, as follows. Let's just define our norm of a vector v to be the square root of the inner product using whatever inner product we have. So now the norm of v is going to be agreed to that it's now the inner product of v with itself square rooted. And in fact, note that if we have v inner product with itself, then this is the Euclidean So if this is the Euclidean inner product, if the inner product is the Euclidean inner product, then this is equivalent to our earlier definition of the two norm. But we're not going to restrict our inner products to always be the Euclidean inner product. However, we will use this norm definition, meaning the norm is going to be whatever we've defined as the inner product, its square root. So we'll use this norm definition with any inner product. And one thing that we might note is if we look at the norm squared of a scaled vector, what's that going to equal? So now you can show this. I'm not going to show it, but you can go home and prove this. Now the norm squared is going to be the inner product of AV with itself. And what have we just looked at? We've seen that we have homogeneity of the first slot, and what do we have in the second slot? We have an AV comma AV. So we have scaled vector V in both slots. We slide out the A from the first slot. What do we slide out from the second slot? Its conjugate. And now A times its conjugate is the magnitude of that scalar squared. And that's now V squared. So with that definition of the norm, now you want to find or scale something and look at its norm squared. You simply scale the vector's norm squared and scale that by the absolute value of the scalar squared. All right, now we're ready to play with orthogonality. Again, you might look at what that has to do with the Supreme Court after class. It's in your book. So a nice little sidebar relative to orthogonality in the Supreme Court. So here we are with orthogonality. Two vectors, we'll call them V and W. Two vectors walk into a bar. No, that's not the bar we're talking about. Anyway, two vectors, V and W, are in this vector space V, are orthogonal. I have a long night ahead of me, so I guess I'm getting a little bit silly. The inner product of V with W, if they're orthogonal, is going to equal 0. And that also implies what about the inner product of W and V? It's also 0. So it really doesn't matter which vector is in which slot. If they are orthogonal vectors, it's going to give you a 0 for the inner product. Here are some observations. That we can make. One is that the 0 vector is orthogonal to every vector in our vector space. You put the 0 vector in a slot, you're going to get 0. 2 is that the 0 vector is the only vector that is orthogonal to itself. Question?
Yeah, so VW, inner product of V and W with V in the first slot is not equal to W in the first slot, V in the second slot, only if it's a complex space, right? For a real space, is it equal?
So now the question is, I think, how can I say something about VW and then the inner product of WV? How can I sort of make those the same? Well, I'm setting them, or they are equal to 0, so that 0 is making them the same. It doesn't matter if I conjugate WV, 0 conjugate is what? 0. So this WV is really saying it doesn't matter where you put these vectors in the inner product. If they're orthogonal, they're going to give you the 0 result. I'm not sure if that was your question or not. But, pardon? It answered whatever it was? Okay. So this is simply saying that if you have two vectors and you want to check them for being orthogonal, it doesn't matter which slot you put them in. And we're actually going to force some vectors to be orthogonal to the others by using the inner product. So we'll set the inner product to 0 and say, what does that force on these vectors? But for now, let's just make 2 observations relative to the 0 vector. 0 is orthogonal to every vector, and 0 is the only vector that is orthogonal to itself. So let's now look at another example to play with this concept of orthogonality. Suppose that we're now in dealing with second-order polynomials, and suppose that we're going to go ahead and use the following inner product. Let's say that it's v minus 1, w minus 1, plus v of 0, w of 0, plus v of 1, w of 1. And now what we want to do is the following. Find a vector w that is orthogonal using this inner product with this inner product. Do you see that it will depend on the inner product, how our vectors, if they're orthogonal or not? So find a w, a vector, a second-order polynomial that is orthogonal with this inner product to a vector v of t, a polynomial v of t that's equal to t plus 1. Well, I guess t plus 1 is our vector. So we now have a vector v, and I'm asking you to find a vector w that's coming to us from the vector space of second-order polynomials that's orthogonal to t plus 1 using this inner product. Suppose we now let this w vector be a generic second-order polynomial. Suppose we say that it's alpha t squared plus beta t plus gamma. So now I have flexibility on all 3 pieces of this second-order polynomial, or this vector w. So now I need to evaluate that at the 3 points. I need to sample w at my 3 points that I've picked for this inner product. And one of those is minus 1. And what does that look like then? Alpha, beta, and gamma are yet to be determined scalars. And I'm now playing in the real numbers, so I'm looking for real values of alpha, beta, and gamma such that this quadratic, or this second-order polynomial, will indeed be orthogonal to t plus 1 using this inner product. What's w of minus 1? Alpha minus beta plus gamma. That's w of minus 1. W of 0, that's gamma, and w of 1. Now let's evaluate v. V at minus 1, 0. V at 0, and v of 1, 2. And now what do I need? Now I need the inner product of V with W, and now it doesn't matter where I put them. I could say W and V. We've learned that, or we've agreed that that's okay. That's now supposed to be 0 for these to be orthogonal. So now I have V of minus 1, which was 0, times W of minus 1, which was alpha minus beta plus gamma. So that coefficient goes away. Whew. That was a messy coefficient. So now we don't have to worry about that. Plus 1 times gamma plus 2 times alpha plus beta plus gamma, and we want that to be equal to 0. So what do we need for W to be orthogonal to V? We need 2 alpha plus 2 beta plus 3 gamma to equal 0. That's all that's required. And there's 30 different solutions, right, to this on an exam. Hopefully I wouldn't formulate, well, who knows how I would formulate it, but there's many possibilities. For finding vectors W that are orthogonal to V. For example, suppose I let alpha be 0. That's allowed. Alpha just needs to be a real scalar. Then that says that I need 2 beta plus 3 gamma to equal 0. So that was kind of fun. I picked one value. Let me pick another. What if I let gamma equal 2? What's beta going to be? I need 2 times beta to be 6, right? Or, I'm sorry, negative 6. So now I need this to be minus 3. Therefore, 1W, let me say W1 of t, that's orthogonal would be minus 3, that's beta t plus gamma, is orthogonal to V of t equaling t plus 1 with the chosen inner product. Just for grins, we can find another one, another W. Suppose now that we let gamma be 0. Now we need 2 alpha plus 2 beta plus 3 times 0 to equal 0. Or alpha now needs to be negative beta. So if we let alpha equal 1, beta is now minus 1, and we now have a second polynomial, a second order polynomial, W2, that's now alpha times t squared, or 1 times t squared, minus beta times t, or now I have t minus 1. And that is also orthogonal to V of t equaling t plus 1. And if you wanted to, you could check this, right? We could say that, well, V of minus 1 is 0, V of 0 was 1, and V of 1 was 2. w of minus 1 for this w is 2, w of 0, 0, and w of 1. So that now, if I looked at v inner product with w2, a lot of things collapse. I have 0 times 2 plus 1 times 0 plus 2 times 0, and that's equal to 0, which is what we wanted, right? We needed it to be orthogonal. So now, let's look at something you've probably not seen. Yes?
Is it accurate to say whether or not two vectors are orthogonal depending on the definition of the inner product?
Yes. So now the question or the comment was, does orthogonality depend on the inner product? And the answer is yes. So however, we could have used a different inner product to find a different w that would be orthogonal to that same v. Okay, so now let's look at something you've probably never seen before, so I apologize, but maybe it'll be nice to learn for the first time. The Pythagorean Theorem. That was another attempt, but it wasn't very funny, so we'll move on. So the Pythagorean Theorem. If u and v are orthogonal, and now we know what that means. If u and v are orthogonal vectors in our vector space V, then if we look at the square of the norm of u plus v, that's equal to the sum of the square of u's norm plus the square of v's norm. Or a squared plus b squared, that's on the right, is equal to c squared. That's if u and v are orthogonal. And now we have a way of demonstrating that based on our understanding of inner product. So that now if I wanted to look at the square of the norm of u plus v, you know how to produce that based on our definition of norm. Our norm was defined to be an inner product square rooted. So here we're not square rooting because we're squaring, so now I simply take the inner product of u plus v with itself. And what can I do now? I can now use the additivity of the first slot to now simplify this a little bit. I can say, oh, I have u comma u plus v plus the inner product of v with u plus v. And now I can work with what? The additivity of the second slot. I know that's true. So now I can use the additivity of the second slot to produce the inner product of u with u and the inner product of u with v. That's the additivity of the second slot. And that worked so nice, let's do it again. So now we can do it again with the second one. So now I have v with u, inner product, plus v with itself. And this now is using the additivity of the second slot as well. What did we assume? We assumed that u and v were orthogonal. And what does that give me? Now I know what those two inner products are. If u and v are orthogonal, those two vanish, or those become 0. And I'm left with the inner product of u with itself plus the inner product of v with itself, but that's just the norm of u squared plus the norm of v squared. And that is another way of validating the Pythagorean theorem. And that's based on what? The Pythagorean theorem is using this right angle when we use it. It's based on a right triangle. Yes?
How do you apply the first slot?
So how did I apply the first slot? Very carefully. So first slot additivity, did I make a mistake? So now what I was doing is I was looking at this and saying additivity of the first slot, I now need to look at this. So now that gave me this. And then the last one, this one, was right there. And then I did the same for the second slot. And in fact, did I have to pick an inner product to show this? No, I didn't have to specify a particular inner product to prove this Pythagorean theorem. All I had to assume was that the vectors u and v were orthogonal. Then orthogonality might depend on the inner product, but that's now assumed with u and v. So let me just state that. Note, this result did not depend on the inner product. I just had to have orthogonality. Yes?
So if I had two vectors that were orthogonal in multiple different ways of taking the inner product, could you mix and match doing this? Like if I had v and w and I have two ways of taking the inner product, and in both of those ways they were orthogonal, and I wanted to do Pythagorean theorem, could I take the inner product of v with itself one way and u with itself the other way and have that be the same?
Oh my goodness. Did anybody hear that question? So let me see if I can paraphrase it. I'm exhausted just listening to it. What was the question? So the question, I think, was, can we mix and match inner product definitions with the Pythagorean theorem? Meaning, if I now have two vectors, u and v, and they're orthogonal using this inner product A, and they're also orthogonal using inner product B, can I somehow shuffle around which inner product I use where in the Pythagorean theorem? I'm going to say no. I wouldn't rely on that. I would preserve the inner product, because now you're saying the inner product, but you can find a counterexample, or you can prove me wrong, but I'm thinking, I haven't thought about this because I'm very structured. I follow the rules, so if somebody gives me an inner product, I stick with it. I don't start going over to B and say, oh, you're on B, let's go to A halfway through. So if we're using one inner product, I would use that and say, okay, here's Pythagorean theorem with that. If I want to use B, then I have to use it throughout. That would be my take on an answer to your question. But what we want to be thinking about now is, if somebody gives you an arbitrary vector, let's say u, and now they say give you another vector v, we want to now say, oh, how do I make this vector u out of some scaled version of v? Maybe I get it, well, maybe it wasn't too hard. I scale it a little bit, and then I try to get another component that's orthogonal to v. So an orthogonal decomposition, that's where we're headed now that we have, and this looks like really Pythagorean theorem, doesn't it? We now have a squared plus b squared equals u. So we are going to try to find how do we scale v such that we can decompose u into a component of v with an orthogonal vector to v. Orthogonal decomposition, that's where we will pick up the next time. And I didn't